So Jacqueline Campbell is a PhD student at UCL's Mars Space Science Laboratory, researching dynamic features on the Martian surface to look for signs of habitability. Today, Jacqueline is going to give us an insight into some of the major challenges in planetary science and what makes the mission to Mars successful. As always, there'll be time for you to submit questions at the end of Jacqueline's presentation, so please do use the chat box in the bottom left-hand side of the screen now, and I will ask them on your behalf at the end of the presentation. So thank you for your attention, and please stand by for this webinar will start shortly. Hi and welcome everybody, good afternoon. It's nice to be here presenting to you, so thank you very much for the Institute of Environmental Sciences. As Rihanna said, I am a PhD student, and I currently look at dynamic features, anything that's changing on the surface of Mars on a sort of more regular basis than we thought it might change, which might have been over millions or billions of years. But I look at things that change on a seasonal basis. And my background is Earth and Ocean Science, was my bachelor's at University of Brighton. And I was very interested in remote sensing and satellite imagery, geochemistry, and I'd also done a little bit of astrophysics as well. But planetary science is a really good discipline if you're from any other background other than just physics, because there's all sorts of different knowledge bases and skills that you need to be able to examine the planets and the different types of planets and moons that we know about just in our own solar system. And we're finding out now more and more about other planets and other solar systems too. So whatever your background in science, there is room to do planetary science. I was a mature student when I started, and I was, sorry, just had a message saying the sound was a bit faint. Hopefully you can hear me a little bit better now. I'm a mature student. I started my degree when I was 31. Before that, I was a train operator driving tubes on London Underground for 10 years before I decided to want to go into science. And so I left that and went part-time as a carer for autistic charity, and did a lot of care work and science stuff for different people with different needs. And then I started my undergraduate, and now I'm doing my PhD. So whatever your background or whatever age you are, there's always time to get into planetary science as well. So I guess we'll kick off now with the scientific content. And I wanted to get some thoughts from you guys listening about why Mars? Why do we want to look at Mars? I mean, Venus is closer and more similar in size to Earth. So what's so special about Mars? It's obviously a lot harder to get to than the Moon. So any thoughts you have on why we want to visit Mars as a scientific target for landers? I'll just throw out a few controversial things of why not Mars. It's really cold, it's really dry. It can take up to 2 years to get there when it's at its furthest away, and it's quite difficult to communicate with when it's far away compared to something like the Moon or any of the satellites just orbiting Earth. There's no constant liquid water on the surface, at least, that we know of. So yeah, in lots of ways, it's not a very good target. But why might it be a better one than some of the other planetary bodies? So see, Pete Collins has said it's got an atmosphere and some kind of active hydrosphere. Yeah, so that's a really good point. It does have an atmosphere. The atmosphere of Mars is about 1% of the density of the atmosphere of Earth. So it doesn't have very strong winds. You might have seen the movie The Martian, where stuff blows around and people get injured. Don't worry, that's not a spoiler, that happens right at the beginning. But that wouldn't really happen on Mars. The wind is not really strong enough to blow anything substantial around. Instruments on the lander, especially the use of UV visible spectrometer. So this is really interesting. So there's a lot of UV light that reaches the surface of Mars because it doesn't have an ozone layer like the Earth does, which is very bad if you haven't got factor 1 million sunscreen, and really bad for any life on the surface. But interestingly, when we look at Mars, we think that it used to have a much denser atmosphere, and it used to have liquid water on the surface for very long periods of time. There's lots of evidence of river channels and lake beds and chemical evidence of long periods of standing water. So although it might not look like the most habitable place now, it probably was quite similar to Earth in a not too distant past. In its early history. So that's interesting. And also there's been recent discoveries of possible transient liquid water on the surface, and most recently some radar data looking at underneath the South Pole, which looks like there might be a permanent stable body of water there. So NASA's kind of mantra is follow the water when you're looking for things on Mars, because we think that water is probably quite important to how life develops and stays alive. So keep an eye on your questions, because I can see there's some more coming, but I'm just going to give you a little brief history of some of the observations of Mars. So this was by Huygens, a scientist, in 1659, looking at Mars, and already he could see that there were some surface features. It wasn't just a uniform blob. But funnily enough, at other times people might look at Mars and it would seem completely featureless. So that's interesting. If anyone has any thoughts on why that might be the case, please let me know. But when they did see features, this is a map by Schiaparelli, and this shows lots of different networks and channels. And obviously this was done with quite a basic telescope in the 1870s and 1880s. And you can see that these look almost quite sort of artificial and human-made. And it also led to a little bit of confusion in the translation of the word for channel, which is canali in Italian. And when this was read by an American astronomer, Percival Lowell, he thought that it meant canal, and then he drew a map that was even more looked like a tube map or something like a metro map. And this led to a lot of speculation about whether or not there was a civilization on Mars, and Lowell had this idea that there was a dying civilization there that had built all these canals to try and move melt ice from the poles and bring it to the dry equator to save this civilization. And a lot of our sort of popular culture of aliens and little green men and War of the Worlds and all this sorts of stuff, and lots of people saying that UFOs came to get them. It all really is based on this kind of early observations of Mars and the idea that there might have been these straight channels. But as cameras have improved, we've started to see a lot more different features on the surface. I'll move on to the next one. Does anybody know what the first successful mission to Mars was, and roughly when it was? So I'm going to move and tell you what it was. It was Mariner 4 in 1964, with just a flyby. And so this literally just sped past Mars and had a look at what it could see. And this is an image from Mariner 7, which was a couple of years later. And you can see there's not really much there, not much detail at all, but you can see a nice bright patch on the bottom of the planet there, which is the South Polar Cap. And Mars does have two permanent polar caps, just like Earth does, as well as lots of ice buried in various places and in permanently shadowed craters all over. So it does have a lot of water, just not that we know of, not a lot of liquid water, although recent discoveries might challenge that. But we can see already by Viking Orbiter, this is a digital mosaic of Viking Orbiter, which is only 1975, a few years later. We're starting to see a lot more features here on the surface, and you can see there that big feature right across the centre there, which is Valles Marineris, which is a huge canyon, which makes the Grand Canyon look like, you know, a crack in the wall. It really is huge. And also they've seen a lot more features just up here on this side. You can see part of the Tharsis region, which is a bulge where there's been lots of volcanism in the past, and you've got various very tall volcanoes there, big shield volcanoes, the tallest of which is Mount Olympus, which is about 3 times the height of Mount Everest. So it's about 27 kilometers tall, which is just unbelievable. Although to look at it, it doesn't look that high. If you were standing on it, you might think you were standing on a flat plane, because it's a very shallow slope that results from no tectonic plates on Mars. So you only get shield volcanoes that just build up and up and up in the same spot over a hot spot, rather than island chains, for example, like Hawaii we have on Earth, or the Canary Islands, where the plate moves and you get a series of volcanoes as the plate moves across. This stays in one spot and just builds and builds and builds, and makes a big low gradient shield volcano. But it's still very interesting and very high topography, so that can be quite useful if you're trying to look at differences in atmosphere, or trying to remove the effects of atmosphere when you're interpreting data. You can take readings from the top of Mount Olympus and from the base of Valles Marineris, and you can pretty much remove all of the atmospheric interference from that. So that's quite a useful technique. So we thought Mars was quite dead for a long time, until we started to get better cameras. And the best camera we have at the moment photographing Mars is the HiRISE instrument. And I strongly encourage you to look up the HiRISE, spelled HIRISE, stands for High resolution imaging science experiment. And if you go and have a look at the website for that, there's all sorts of beautiful imagery. And I've just given you a few here to look at. So on the top left, just here, that's these recurring slope linei that have been in the news the last few years. In 2015, there was a paper published that posited that these might be the result of transient liquid water flows moving across the surface that were able to remain liquid because of salts in them, so they were essentially brines. But that is quite debated. There's some controversy about whether or not it's a dry process or a wet process, or if it could be CO2 rather than water that's responsible for it. So that's still something that's kind of an ongoing debate. But it definitely shows seasonal changes with lengthening and shortening of these dark streaks in spring, summer. So they're pretty interesting. In the middle here, we've got a dust devil. So they're really common, and there's been a few of those captured on video by the rovers and from orbit. And they can get really, really high because of the low gravity on Mars. They can reach sort of tens of kilometers high and just spin around and leave some pretty tracks on the surface. So one of the biggest surface changes we see, most common surface changes we see are dust devil tracks. And if you're lucky, you might catch one in action. Over here on the top right, you've got some dunes. So you see a lot of dune movement. There is some debate over whether or not some examples of dune movement are just pictures not being quite matched up, and so when you look at them, it looks like the sand is moving. But when you have a big enough area with some other rock or something that you can see staying stationary, you can certainly see migration of dunes in much the same way that we see on deserts on Earth. Over here on the left, this is just a picture of the crater, and we've seen new craters appearing on Mars. So there are examples of new craters forming and then uncovering ice, and then you see that sublimating away and stuff. So quite a lot of surface change from external things as well. Over here on the right, this one are these are fans that you get around the South Pole, which are the result of light shining through CO2 ice and warming up the surface below, and then you get like a pocket of CO2 gas that explodes and shoots dust everywhere, and then all the ice melts in the summer, and you're left with these fan and spider-like patterns on the surface. And these are pretty cool because they can tell you something about the direction the wind was blowing at the time that the dust was deposited, and they change seasonally, so they're quite an interesting phenomenon, and not much is known about them. On the bottom right here, this is Swiss cheese terrain, because apparently it looks like Swiss cheese. And this is one of the things I study, and these are really unique sublimation features which occur on the South Pole only of Mars, where the permanent CO2 ice cap in the spring and summer heats up and goes straight from the solid to the vapor phase, and then redeposits each year, and you get these widening pits that accumulate dust around the edges and are pretty interesting. So I study those and look at the dust composition on the rims of those to see if there's any sign of any organics there that might have been protected from UV within the ice. In the middle here is quite interesting. This is a gully that was, these pictures were taken by HiRISE a couple of years apart. And on one side you can see just one straight gully, and the second one you can see there's been some sort of change there. So this is one of the arguments for present liquid water, but again, some people say it might be dry processes. And I think on the bottom left here is one of my favourites. This was taken by the HiRISE camera just above the North Pole, which has lots of blocking slabs of water ice. And they actually caught an avalanche in action. So this is the exact moment that an ice block falls down and crashes into the dusty surface and creates a big cloud of dust and ice. So the odds of catching that are quite low, I think. Although it does happen quite regularly, catching that with a camera as good as HiRISE is quite difficult. So that's a really cool one. So landing on Mars, what are the advantages and disadvantages of landing on the planetary surfaces, and what are the challenges with Mars specifically? Please feel free to leave any comments in the chat box if you've got any ideas about what the advantages are. First of all, I'll talk a little bit more about my work here on Earth, and then if anyone's got any ideas why that might be well supported by going to the surface, then please let me know. So obviously we do a lot of experiments on Earth to support interpreting the data that we get from telescopes and orbiters. So one of the things that I do is I go to the laboratory and use a chamber that they call a Mars chamber, which emulates the conditions of the surface of Mars, bringing the pressure and temperature right down, and then even using UV radiation to simulate exactly what it's like on the surface. and you can put various minerals and organics and chemicals in there and try and work out what would happen to them. And then you can compare this to data that you get from orbit. Also, there can be physical experiments as well, looking at how the minerals and how the sand and stuff might move, how things form. You've got people that are doing experiments with crater impacts, so simulating crater impacts on the Martian surface, trying to work out how it develops morphology. So the advantages of going to the surface is that you can get in situ information about exactly what is going on the surface. We can use orbiters to use things like infrared spectroscopy to find out what the composition of the surface is, but you're limited in terms of your spatial resolution. You might be limited to, I think the best is around 20 meters per pixel. And so if you're trying to look at any fine scale features like the rims of those cheese terrain things that I look at, you're quite limited. So it would be a huge advantage to be able to go down there and take a physical sample. Unfortunately, there are lots of problems with landing on Mars, not least of which is the surface is quite rough and bumpy in many places. If you wanted to land on the south pole of Mars, you've got huge scarp walls that are like 10 meters deep, and if something landed badly on the edge of one, it would fall down, and we can't predict exactly how something will land within meters on terrain like that. That's quite changeable. Another big one comes back to the density of the atmosphere. So if your atmosphere is not particularly dense, then it's quite difficult to use the atmosphere friction to brake your vehicle, use aeroshells to brake. And obviously, we know that there are issues with things burning up and getting really hot, and that still happens with the speed that some of these things come into the atmosphere of Mars. But it's quite difficult to use parachutes and aero braking to stop in the atmosphere of Mars as you would on Earth. So that's another big problem. Then you've got the problem of trying to communicate back to Earth. As Mars moves away from us, it can take up to 40 minutes round trip to get your information to Mars and back. And so if you're trying to drive a rover in real time, this just isn't really feasible. Sometimes when it's closer, it might only take you sort of 8 or 10 minutes to get the information, but that's too slow to tell a rover, go left, go right. You can't go up that slope. So we have to build into rovers ideas about using AI about what they can safely do, and they will make their own assessments and decisions. So that's something that's getting better and better, and allowing the rovers to move autonomously and cover more ground in a day without waiting for us to send them information. So yeah, Mars can be a difficult one. Another big problem with Mars is what I mentioned earlier about occasionally when you look at Mars, it looks completely featureless, and that's because it has regular global dust storms. Although the wind is not very strong there, the gravity is lower, so it can pick up fine particulates and make a global dust storm. And without any vegetation or oceans there to kind of regulate climate in the same way that we have here, you end up with just a worldwide dust storm that stops any sun getting to the surface. And you might have seen recently in the news that the Opportunity rover is asleep, and we don't know if it's going to wake up while it's waiting out one of these dust storms. And often if you've got anything with solar panels, it can cover the solar panels and stop you getting light, and your machine has to go to sleep. So landing on Mars, one of the first things that landed on Mars was the Soviet Union's Mars 2 and Mars 3 landers. So Mars 2 was a hard landing and just crashed into the surface. Mars 3 was a soft landing. But arguably the most successful of the early landings was the Viking 1 lander, which up until recently still has the record for the longest mission on Mars. It was overtaken by the Opportunity rover not too long ago. And yeah, this sent back lots of really interesting information about the mineralogy and about the chemistry and the climate there. It was fairly basic, didn't have a lot of instruments on it, but certainly enough to know what was going on. When this came there, it used an aeroshell for braking, and then retro rockets to stabilize itself, then a parachute. And again, parachutes can be quite problematic because there are quite high speed winds, although they're not strong in terms of the density of the atmosphere. They can lead to problems with the parachute doing things like what they call squidding. So there's a whole bunch of tests they do over at NASA JPL with various wind tunnels and parachutes to try and see how they'll react in the Martian atmosphere. And I know with the Spirit and Opportunity rovers, they had a lot of issues with the parachute squidding and just flapping around and wouldn't open properly. And then your Viking lander comes down and opens its 3 legs and then uses retro rockets again to stabilize. And on board this, it had quite a few instruments, but when you compare it to modern rover missions, it was fairly basic. But it had mass spectrometer, pressure, temperature, and density sensors on the way down as it lands, and then it had cameras and then various biological tests. So Viking really wanted to find out if there was life on Mars. And there was some controversy at the time because one of its experiments came back positive for life, whereas all the rest have definitely no, there's not even organics here. There's still a few scientists that believe that that might have been a positive sign for life, but it's much more likely that it was just some sort of local chemical phenomenon to do with oxidation of the surface, and that it gave a false positive essentially. Although there has been recent reanalysis of the Viking missions to find organic materials, and we know that there are organics and various salts and chlorates and things like that on Mars that are of interest to astrobiology, but there are very few people now that believe that life was found with the Viking mission, but at the time it was kind of a big deal. Next, we're going to talk about the Mars Pathfinder mission, which is a fantastic mission and came up with a really novel way of landing its lander and its accompanying rover. Again, you might have seen, if you've seen The Martian, this is in that movie, and this little rover is really small. It's just like the size of a sort of large remote-controlled car that you might get. But the whole system was large enough that in order to land it, traditional retro rockets and parachutes and aeroshells weren't enough to slow it down. So this was the first mission that used basically a load of airbags in a big sort of ball or pyramid wrapped around the lander and little rover, and then just bounced its way to safety. This means that maybe it's not quite so accurate where you land because you can just roll and bounce, and with the lower gravity being at about sort of just under 40% of Earth, you can bounce for quite a long time. But yeah, it worked really well, and the rover got to go off and do various things, and down at the bottom there you can see a nice panorama from the Pathfinder lander, which is pretty cool. So Pathfinder it really lived up to its name. It paved the way for landing much heavier stuff on Mars, so that's a really important one. Couple of failures now, and I say failures, obviously it's not a good thing when something goes to Mars and doesn't send the information back, but often they're only really partial failures, or we learn something much more from doing them. So it's costly, but you still learn and you want to do things right. So the Mars Polar Lander, they think that the thrusters didn't activate. So this is an artist's impression of it on the right. They think the thrusters didn't activate in time, so it just had a hard landing and just crashed. Nothing was heard from it. Beagle 2, they think that this is the solar panels opening up here on the model, and they think that only maybe 2 of them opened and it just couldn't get enough power. So we didn't hear anything from that, but it did land safely, we know that. And then the Mars Climate Orbiter was an exercise in why you should do protocol properly, because Lockheed Martin were responsible for dealing with some of the thruster information, and NASA, who took the blame for it by not doing their checks properly, they didn't check what units had been used, and so Lockheed Martin were using some imperial units essentially of using pounds, and the NASA people were using Newton seconds. So when they worked out how long to fire their thrusters for in order to stabilize it, the software worked it out incorrectly because of misuse of units. And so this is why protocols and checking everything are really important, because it just died basically. So they reckon part of that is on the surface, but it's in bits probably. This is an image of the Beagle 2 lander that didn't open its solar panels. And on the left here is the original image, and on the right here, although it's not much to look at, but it's certainly an awful lot clearer, and you can actually see the shape of the lander. And this is using a method called super resolution, where you can take several images at a lower resolution and combine them and enhance them, which they always make look very easy in movies when they just get like the worst picture ever and then just make it really clear. But it is actually really hard to do, and this is by my colleague Yutao, who's at my laboratory. So they've got a nice, much clearer picture of where Beagle is now. And they can use this to do other things, to find out more information about where landers are and get exact position for things, and also just examine features in much more detail than it might otherwise be possible with older imagery, which is particularly useful for looking at changes over time, because we've got the nice new high-rise images from the last 10 years, but what if we want to compare that to something from 40 years ago? We're limited by the technology available at the time, but new techniques like super resolution can enable us to look for changes over decades, which is pretty cool. So I think this mission, the Mars Exploration Rover mission, or MER, is arguably the most successful space mission of all time. I'd say that Voyager is probably up there with that, and obviously the moon landings. But in terms of the amount of data that went back, and certainly the longevity of missions to Mars, this is the winner. So there were two identical rovers, Spirit and Opportunity, that landed in 2004. And they had various cameras and close-up images, the rock abrasion tool to scratch rocks, and a couple of spectrometers. And they are solar powered, and they've got 6 wheels, and they're reasonably small and trundle about on the surface. And yeah, they were dropped in 2 different places. And I'm going to talk first a little bit about Spirit, which was the first one to give up the ghost a few years ago. So I was talking to you earlier about those global dust storms, and here's an example of the same year. This is in June 2001 left and September 2001 on the right, and you can see the difference in what you can see on the surface there and how difficult it might be for the sun to get through to any solar powered things, and this can be a real issue. Fortunately, they're quite, well, I won't say easy to predict, but they are sort of a regular phenomenon, and we do kind of know what time of year they're going to happen, and we try to time missions not to land when there's a dust storm so we can't see what's going on. But when you've got a long-term, years-long mission like the MER rovers, then these are going to happen periodically, and you'll lose contact with your rover. So this is a picture of Spirit when it had dust all over its solar panels, and you can see barely distinguish the solar panels from the ground below. But there were various ideas about what they could do about this, and one of the things when they were designing this was to come up with some sort of like almost like a plasticky cling film that went across, that was on a roller that you could just go and roll it across and like get rid of the dust. But this just was too many working bits. It was too heavy and just too fiddly. And so what they try to do when the solar panels are going to be covered is get themselves in a position where they know the wind direction is going to blow it clean again. And more often than not, you will see that they can get themselves in the right place, and when the dust clears and the wind blows, it just gets rid of all the dust and your rover comes back to life again. Unfortunately, the Opportunity rover, which is kind of in this position now in a global dust storm, didn't have an opportunity to get to the right angle and get itself sorted. And also its battery runs so low that its clock has an error, so it doesn't know what time it is. And so they're waiting for it to wake up once the storm clears, and then it will probably beep at us, but it doesn't know what time it is, and so they don't know when it's going to beep. So they're just on permanent listen out now and waiting for opportunity to just beep when it feels like it, basically. So this is where the Spirit Opportunity landed in Gusev Crater, and here a lot of you might be familiar with digital elevation models or digital terrain models, if you use any of that for any of your work. But essentially it's height data, and there are various ways to get this, and one of the most common ways to use this for Mars is the data from the MOLA mission, which is the Mars Orbital Laser Altimeter. And this was an instrument that went around and fired lasers at the surface and timed how long it took them to get back, to get global height data for the entire planet. And this is really, really useful, but it's fairly low resolution because it's global, so in the hundreds of meter scale, which is really useful for getting a roundabout idea of where you want to go. And when you see most sort of color height maps of Mars, it's often the MOLA data that they're using. But if you want to have a really detailed look at where you're landing, then you'll probably want to get much higher resolution, and this can be done using stereo imagery. So you can either have an orbiter that goes around and takes 2 different images from 2 slightly different angles at different times, or on some of the cameras, like on HRSC, which is on ESA's Mars Express, and on the new ESA Trace Gas Orbiter has a camera called Perseus, they can take their pictures at pretty much the same time as they go past, which is especially useful if you're taking pictures of a dynamic feature, because often to get get your repeat image at a slightly different angle, you might have to wait a year or two. And in places like the South Pole, there'll be massive changes in the topography in between those two times. So having cameras like that can take simultaneous stereo imagery and then use that to build a 3D model are really useful. So yeah, we use a lot of 3D models to select landing sites and to see what the topography is going to be like where it lands. And when we get to the Opportunity rover, you'll see that sometimes it doesn't go always as planned. So the Spirit rover was doing really well and it's trundling around for quite a long time. But then one of its wheels got stuck and everyone was like, oh no. But it actually turned out to be quite useful because here at the bottom you can see the dead wheel couldn't turn and just started like dragging along and exposing stuff. And it actually exposed some really cool and interesting minerals, and I think this was sulfates that it uncovered when it was dragging along, and that just wouldn't have happened if it hadn't broken down essentially. And then it eventually came to a stop and stayed stationary. But again, when they plan rover missions, they kind of planned for this, and then it was able to do more in situ experiments that it could take longer to look at things than it would do if it was trundling around from place to place. So it was still pretty useful until it gave up the ghost then. And this was the traverse map of Spirit. And this covered about, it's not very far when you think about it, but it's 7.73 kilometers. And this is one of the arguments for why we really want to send people to Mars at some point, because when the lunar Apollo astronauts went to the moon and they had the little moon buggies, they covered more distance in 3 days than you can in 10 years with a non-human piloted rover. So you definitely get a lot more work done, but obviously it's much safer to just send robots for now until our technology improves. On to the next one. So this is, sorry, I've got the slide wrong. This is actually the Opportunity, the Meridiani Planum. This is the longest running mission to Mars. Over 5,500 sols, which is a Martian day, which is pretty close to the same length as an Earth day. And so it wanted to land in Meridiani Planum because it was thought that this was a floodplain, or at least it had some standing water on it for some time. But when it landed and bounced, because it's also used that airbag system similar to Pathfinder, you can see here, this is the first bounce of the ball. This is the back shell on parachute where it landed, heat shield impact site. And then it bounced and rolled and rolled and rolled and went straight into this crater. And there's a really funny YouTube video of the principal investigator for this mission, Steve Squires, talking about this and how it was a hole-in-one. And you could never have done this if you tried, but they got the data back, and it's quite amusing to see that it just bounced into here. And then they were like, is it going to be able to get out? How steep is the walls of this crater? But fortunately, it was fine and went on to be arguably the most successful mission of all time. And here are some of the things that that the rover found. So it found what they think is the first ever meteorites to be discovered on Mars. So this looks like it's come from elsewhere in the solar system and landed on the surface of Mars. We find quite a lot of meteorites from space on Earth, obviously, and even Martian meteorites we find here, which appear to be where there's been some sort of collision with Mars and a Mars rock has then landed on Earth. A lot of these are found in Antarctica because it's easy to see new rock falls landing on like a big sheet of ice rather than, say, fell into the sea or in a forest or something like that. But yeah, this is what they think is the first ever meteorite to be found on another planet. It also found these hematite nodules here, these sort of like iron spherules here that they call blueberries, which are an example of what you get when you have iron in standing water. And they, as far as you know, they can only really be produced when there's long periods of stable standing water. So that's another compelling argument for there having been water on Mars. Over on the right here, this is just a sort of semi-mocked up, but using real imagery of the rover itself and the background of what it would look like trundling about on the surface. And this is a really nice little panorama looking at all these nice sort of platey terrain here, which looks really similar to what you see on Earth. And in my mind, there's no doubt that there were long periods of standing and running water on Mars. We've seen there are lake deposits and sedimentary deposits, clays, these hematite nodules, and riverbeds, and all sorts of examples that there was long periods of standing water on Mars. But whether or not it had a global hydrological cycle like on Earth with, regular rain and stuff is another matter. It might well have been more, and there is evidence for sort of chaotic flash flood events where maybe ice is suddenly melted by some seismic activity or volcanic activity or an impactor, and then you just get huge outpourings of water running and then sitting maybe in a crater or something for a long time. Whether or not it actually rained on Mars is something that's still being debated. So this rover was a number of firsts. It drove more than 45 kilometers, which is incredible. It traversed the steepest slope and sat at the highest elevation of any rover, and we're still waiting for that to wake up. So when Opportunity feels like beating back to Earth, hopefully it will come back to life and continue its mission. But it remains to be seen. Curiosity, this is me. I'm in JPL in California here with the Curiosity model, and this is huge. This weighs like nearly 900 kilograms. It's like way bigger than the Spirit Opportunity rovers. It's sort of about the size of a car, like a large car, and it's absolutely jam-packed with various different instruments. Just to give you an idea of the scale, on the left there is the wheel for the little Siorna rover that was going around with Pathfinder. That's the MER Spirit and Opportunity wheels, and this bad boy here is the Mars Science Laboratory or Curiosity rover. And we'll talk a little bit more about those wheels later. Also, I can't remember what it says now, but it does have a little pattern on the track so that when it rolls around, it leaves a little pattern. I think it's in Morse code on the surface. But if you look into that, it's got a little thing, so wherever it goes, it's like leaving itself a little bit of graffiti on the surface of Mars. Also, it's been quite instrumental in how they design future wheels, and I'll talk a little bit more about those wheels in a bit. So this is Curiosity. It's absolutely jam-packed with various different instruments. Too many to go through, but it has, I think, 17 different cameras for various different purposes, for navigation, for science, for looking at itself to make sure it's all right. The SAM instrument, the Sample Analysis at Mars instrument, has been in the news recently because it's found some evidence of organics. But unfortunately, the SAM instrument has to heat things up to quite a hot temperature in order to analyse them. And this means it actually destroys the organics it might be looking at. When the ESA rover ExoMars 2020 goes up, that will be able to look at things in a similar instrument without heating them up, so you'll get a more direct idea of organics. But it certainly had lots of interesting things to look at. It also has a laser, so it goes around and lasers rocks, and then it looks at the spectra of what it's vaporized and then decides if that's worth looking into in more detail, and then it uses it for robotic arms to go and it can drill, it can take little samples of the rock, it can analyze them on board, it can look at the chemistry, it can look at the X-ray spectrometry. It's really quite a sophisticated laboratory. It is a laboratory on wheels, and that's why it was so heavy. And so you might be thinking, well, if Mars Pathfinder and Spirit and Opportunity needed these big airbags to land, then how on Earth or how Mars would they get Curiosity to land safely? And this is, I think, one of the most unbelievable pieces of engineering I think I've ever seen. Just to say as well, one thing that Curiosity doesn't have as a problem is any solar panels. You can see on this picture there are no solar panels there, and that's because it runs on a radioisotope thermoelectric generator, basically using radioactive material like plutonium to keep itself going, which means it doesn't have to rely on solar panels. Obviously, there are other issues with using this. It's a reasonably finite thing, but they can last for a very long time. Other things can go wrong with them, and they can end up damaging your machinery or impacting on your other instruments. But this is what they use for also missions that go out into the outer solar system, like Voyager and Pioneer, because obviously they get so far away from the sun that solar panels are useless. I've just seen a nice question come up there about how realistic is Elon Musk's plans to put 1 million people on Mars in 40 to 100 years. And I'm glad you asked that, because I have actually a relevant slide coming up about what I think is one of the problems with that shortly. So yeah, back to Curiosity. It's a big, heavy lump of a laboratory, and this is how they landed it, which is just unbelievable. They developed this thing called Sky Crane, and when people saw it coming up, they were like, "That's ridiculous. Obviously, it's going to crash. Like everything crashes on Mars anyway, even when it's like a third of the way, and it's been done 1 million times with like various experiments. And what they wanted to do was use a similar initial entry to the planet where you have an aeroshell to slow down and then a parachute to slow down further. And then the airbags wouldn't have been enough to put this big lump of a rover on the surface. So they had a floating platform which works somewhat like a drone might work, but instead of propellers, it has retro rocket thrusters. And then it hovered this little platform, dangling the rover off the bottom on essentially a piece of string. Obviously, I'm simplifying this. They did lots of tests, and it worked very well. But they had a floating platform and then dangled the rover off and lowered it down on a line onto the surface. And then the thrusters fire itself away safely so that it goes and lands somewhere else, and God forbid, doesn't just crash land on the rover. It's just deposited on the surface. And this is actually a really successful thing. It's an incredible piece of engineering. And this is also going to be used to land the next NASA rover, which is confusingly, there are two rovers going up, the NASA 2020 and the ESA 2020 rovers. And the NASA one will use the Skycrane system again, which has helped keep costs to a minimum. And this is another thing that happens quite often in planning these landers and rovers, is that they try to reuse technology like the airbags for both Pathfinder and Spirit and Opportunity, Skycrane for Curiosity and the 2020 rover, because it keeps costs down. And as with Spirit and Opportunity, if you can get 2 for 1, essentially, you're building one, you might as well build 2, and you might as well build 10. And this is something that's used for a lot of other space missions like CubeSat stuff, which is little tiny satellite instruments that go up. And if you're building one, you may as well build 10 because it ends up much more cost effective. So here's a beautiful image of something that Curiosity took, and you can see some of the detail of this is incredible. And much like with the stereo imagery from orbit, you can use Rovergery to build 3D models that you can then pan around in. And there are plenty of different softwares you can use, some of which are free, and there's some sort of public access stuff that you can look at these. And I've seen people using headsets and like phones, the virtual reality phone viewer things to be on Mars, basically. So you can actually do useful geology from using some of these things. Curiosity wheel damage. So yeah, coming back to the wheels, you can see here they didn't anticipate quite how rough the terrain would be on these wheels. So these are thin aluminium wheels, and the wheels can often be one of the heaviest parts because they really do need to be durable and quite big to carry the rover. So they used aluminium for these, and they made it as thin as possible, but they've been taking a real beating. So this is one of the things that will probably factor in Curiosity's longevity as a mission. The wheels will probably be the first thing to go. As a result, the NASA 2020 rover is going to have much thicker aluminium wheels, and the ESA ExoMars 2020 rover will have titanium wheels, which is a bit tougher. But yeah, weight is a real consideration. You have to keep that to a minimum, but you can see it can really damage your entire mission if your wheels just aren't strong enough. So it's as with every space mission, it's a trade-off between what you need and what it weighs, basically. So coming back to Adam's question about Elon Musk putting people on Mars, does anybody know what planetary protection is, what the field of planetary protection is? While I wait for any answers to come up, I'll talk a little bit about what I think about the privatization of the space industry. I think ideally, I don't like the idea of privatizing things. I don't like the idea of people having to pay for data, because currently all of the data from NASA and ESA and other space agencies, vast majority of it is free and available to download from the NASA Planetary Data Archive. And you can go on there and get data from anything back to the earliest missions all the way up until now, and use that data as you see fit. And you can email those people who do it and ask for things, and they'll do it for you for free. And I like that. And you were already seeing with Earth observation missions that are private that people are having to pay huge sums of money. And it means that students can't learn how to use this data easily. People can't use it for purposes that are not particularly lucrative. So, for example, the military will be happy to pay a fortune for certain data. Whereas if you're an environmental scientist, it's like, oh, I'm really interested in like helping otter populations stop suffering from pollution. Can I get this data? And they're like, yeah, it's going to be £10,000. It's going to stop a lot of valuable research being done that doesn't make money, but is incredibly important for Earth. And I can see that might be the case for other missions to other planets. But at the same time, we're seeing more and more cuts in funding to space stuff. I mean, maybe Donald Trump aside with his Space Force, but you know, I'm not hopeful that that's got much scientific focus. But yeah, it's unfortunate that there is a lot of cutting in funding, and then when you are in charge in times like Brexit or some social crisis or environmental crisis, people don't want to spend billions of pounds on a rover. Although I would argue that, obviously space science and especially Earth observation and technology is incredibly useful for people for all sorts of different reasons. But you're kind of constrained by the political will of the time, and you might only be in Parliament for 5 years or 4 years or something. So when you're doing that, you have to see what the public want, and you're on a sort of 4-year basis. Some of these missions take decades to plan, especially to the outer solar system. And somebody like Elon Musk, who's a private individual who might be beholden somewhat to his shareholders, but he can ultimately have a 50-year plan, and that's something that you can't get necessarily when it's publicly funded. So I haven't had anything on what planetary protection is. So planetary protection is about not contaminating the surface of planets, and this is not really that important for when things just go up into space and are floating about in deep space, or really when they're going somewhere like the moon or somewhere that's not particularly thought to have life, but somewhere like Mars, which is a massive candidate for life, and certainly places like Europa or Enceladus around the outer gas giants that we know have liquid water on them. Planetary protection is paramount. And so at my laboratory, one of the things they do there is they build a lot of instrumentation there that gets sent off to space. And we're currently building the PanCam, which is on the ExoMars rover to go to Mars. And all of this has to go through clean room procedures to get rid of any microbes or little critters on there that might survive, and make sure that if anything lands on the surface, it's not going to contaminate what's already there. Because not only from a sort of ethical perspective of maybe contaminating where something lives, but from a science perspective of something like the Viking missions, you might be just reading stuff that's stuck on your own lander, and then you're like, woo, life on Mars, and base your whole career on it, and it turns out you just brought some bugs with you. So they go through a whole bunch of different things to do this, and this is Curiosity in one of the clean rooms at JPL. You can get a sense of the scale of those wheels there. And so it gets cleaned off with various different solutions, and it gets baked to high temperature, and it gets irradiated, and it's all sealed up and sent away. I've got another question. Is planetary protection from the atmosphere against meters and UV? So I mean, yeah, I see what you said there. That's a really good idea about protecting the vehicle itself. So that's another aspect to what you might want to do for your rover, is having it protected from the environmental hazards on Mars. But yeah, planetary protection is literally about the protection of the planet itself. And another question here, extending the philosophy of planetary protection further, do you think there is an argument that Mars, as a culturally significant object for humanity, deserves further protection? Would this apply to the whole planet or just a unique feature like the Valles Marineris? That's a really good question, and I think that for me, I think it would be very important. I think there's a famous Carl Sagan quote that if we do find life on Mars, we should leave it for the Martians. So there's that perspective of, do we have a right to go there and interfere with anything that's living there? So I mean, obviously on Mars we're probably talking about microbes, if anything. But if and when we go to Enceladus or Europa, we might find much more complex creatures living there. Do we have a right to experiment on them, to mistreat them in any way? I would argue we haven't even worked that out ourselves here on Earth. So, the way that we treat the environment and animals on this planet is something that leaves a lot to be desired. So the idea that we will be able to restrain ourselves and have the necessary policy and ethics to think about what to do if we discover some squids on Europa is another thing. And yeah, the idea that could be, what if we find some really important mineral on Valles Marineris and we just don't like to dig it all up? I think that that's something that should be very much considered. And going back to just the contamination, we won't even let the Curiosity rover roll right up to an area of Gale Crater where it is at the moment, called Mount Sharp, to look at the deposit there, because we don't want to possibly contaminate something that very probably had a lot of liquid water. So what about if Elon Musk goes up there with hundreds of people, and they're not trained astronauts in the same way that they might be if they were sent there by ESA or NASA? They're not beholden to the same things. I mean, there are various guidelines that are coming out, but we already have a lot of the legislation around space behaviour, not very well thought out. So space junk is a huge problem. And although there are guidelines on it, nobody really owns it. And I've just had a question actually, who legally owns Mars? It's under a treaty that nobody owns it. So you're not allowed to go there and claim it for any one country. So this means that who's going to stop you? How are we going to stop people from going there and digging things up? Obviously, there'll be scientific interest there as well, I'm sure. But, you know, if something is very lucrative, then I don't think people will pay much attention to ripping it up, because we don't do that on Earth. We don't do that when there are human lives involved here on Earth. So how are we possibly going to control this in space? And if various asteroids or parts of Mars are particularly lucrative to destroy, it could become sort of the Wild West frontier, where we destroy everything there and give no regards to who or what is living there. So just to recap, because we're coming to the end of our time, this is all the landing sites to date on Mars. The red ones are rovers and the blue ones are landers. I didn't talk much about the Phoenix lander, which landed up here in the northern lowlands here. This one was pretty cool. It found some interesting perchlorates and things that are of interest to astrobiology. And down here, Deep Space 2, this was another failed one. This landed on the surface and was supposed to penetrate into the surface and send data back, but unfortunately it didn't. So coming up next, we have the two rovers from NASA and ESA. One at the top is the RTG radioisotope powered NASA one, which is very similar to Curiosity, but a little bit heavier. Again, it's going to use Sky Crane, and that's scheduled for launch in 2020. And down at the bottom here, we have the ESA one, which is solar powered and a lot lighter, and that's scheduled for 2020 as well. We normally send missions to Mars roughly every 24 months, because that's when Mars is closest. So that's why it tends to be on a sort of 2-year scale. Finally, this is just the lab I work at. If you want to find out more about the instruments that are developed and built at UCL's Department of Space and Climate Physics, then please have a look at the Mullard Space Science Laboratory website. This is me doing some experiments with some organics there. And if you've got any further questions or you want any advice about careers or anything like that, then do feel free to drop me an email. I'd be more than happy to help if I can. And in the last few minutes, I'm happy to take any questions that anyone has. Thank you very much.
Brilliant, thank you. That was really interesting, and great that you answered those questions that came in. Going in further. I'm just curious to know how long it takes to build something like Curiosity from day one to get it launched. How many years is that?
Yeah, I'd say for these sorts of things, I'd say it's about roughly sort of years to decades. And if you're including conception, because obviously these things build on older ideas, there'll be sort of an idea to do something, and then they'll put out a call, and then a load of competing people will come together. I mean, this is more NASA I'm talking about. ESA is a little bit different, but NASA is quite competitive and will put out this call, and several groups will come together, all come up with a concept, submit it, try and sort of poach people from the different groups that they want to work with them, and then there'll be like a review that looks through and goes like, yeah, this is the one we want to build. And often that goes on for years and then ends in nothing. So people, because they have to decide what's going to work, and although it might be expensive to come up with all these ideas, you don't want to go through and build something that's not going to work. And I thoroughly recommend, if you want to know about the whole process of designing and executing a mission, reading this book called Roving Mars by Steve Swile, who is the principal investigator for the Spirit and Opportunity rovers. And he was, I think, that one, he was working on it for close on to 20 years. He was working on that, and it was, you know, his baby, and he worked on it so hard, and there were so many times when it nearly got kicked back to the drawing board. And it's a very emotional read, and it really makes you tired just reading of all the hoops you have to jump through to do something as complicated as going to Mars. So, yeah, read Roving Mars if you want an idea of how absolutely exhausting it is to design a mission, and how many people are involved. Thousands and thousands of people are involved in it.
So these two going up in 2020 have been talked about
for a very long time.
Years.
Yeah, and I'd say built-wise, it's maybe closer to sort of 5 years, I guess. But again, you have to, ExoMars 2020, for example, was supposed to be ExoMars 2018, was pushed back, and it has to be 2 years because of the window for launching, because some of the instruments weren't quite ready to go, and there's no point sending something that, you know, that's not going to get money's worth. And then you've got arguments. Once you've even got, like, let's say the rover or the lander design, then the people who want the different instruments have to fight it out, like what instruments you want it and stuff. So it's all very complicated, yeah.
Okay. You might want to add this, just getting some of our members to just having school outreach talks. That's just something.
Yes, I already do school outreach talks. So if anybody's interested, I also work with a charity called SpaceLink, and we have a website and YouTube channel, and we arrange to do live webcasts and school talks and visits and stuff to schools. We also have awards we give out for kids. So if anybody wants to get involved in SpaceLink, if you have a school or organisation that you want young people to receive a talk from, or if you want to give a talk on something, if anybody is in environmental science and wants to talk about that sort of thing, you can give me a shout. But yeah, check out SpaceLink, and I do quite a lot of outreach talks. And yeah, thank you. Someone said it was cool, and someone else said it was interesting. So thank you very much. It's very much appreciated. I hope it wasn't too much of a swift journey through Mars history.
I think it's absolutely brilliant. It's really, really interesting. Yeah, echo what those comments have said. Yeah, hopefully we can do something again one day when you've got more data to talk about.
Yeah, absolutely. Yeah, I'd be more than happy to. My current research is Mars, but it's, I know a reasonable amount about most of the sort of astrobiologically interesting bodies in the solar system, so ice moons, comets, and stuff like that. So yeah, if anyone's more interested in the astrobiology stuff or in just general kind of geology of the solar system, then yeah, I'd be more than happy to come back.
Brilliant. Great. So yeah, watch the space and hopefully there'll be another one to follow.
Thank you so much, everyone.
Yeah, thank you all for logging in, and just remember that you can log this as